Anna Hoffman, and welcome to this episode of Data Exposed Live, especially something old, something new. And I'm joined today by Buck Woody.
How you doing, Anna?
I am doing well. I'm interested to see what we're doing today, and I'm equally interested by your literal green screen.
Yeah, they said the software thing on the computer said to put the green screen on, so I did. I've got green. Am I doing it wrong?
Yeah, I mean, usually then you put something on the green screen, but that's okay.
Like a piece of paper or something, or what do you want me to?
Yeah, something like that.
Okay. All right.
Maybe next time.
Maybe next time. All right. Well, let's talk a little bit about this particular episode: reduce, reuse, and recycle.
Why is it called that, by the way? I meant to ask you that before we went live.
Yeah. So you're not at all prepped.
Well.
No, that's awesome. No, that's fine. That's fine. We'll figure it out as we go. The reduce, reuse, and recycle. That was something that was very popular in the early 70s when sort of Earth Day started and all that sort of thing. That became a thing you would say: reduce, reuse, and recycle. And we're going to do the same thing with data.
Okay, got it. Sounds good. I'm looking forward to learning how that relates to this. Okay. I just wanted to, before we get started, remind everyone to ask questions from wherever you're streaming from, whether it's Twitch, YouTube, Twitter, or Learn TV. But we have some special stuff happening today, especially in the beginning of the episode, that is going to be specifically on Learn TV. So if you want to participate in that bit, you need to head over to Learn TV pretty soon. But we'll be looking at comments, we'll be looking at questions. So as you have them, please put them in. If you have comments to make about Buck's shirt, which I'm also not sure is the deal with that today, but let's take a look at that. What is going on there, Buck?
It's well, Anna, it's math. You don't. I mean, really? You don't. I mean,
well, yes,
it's B greater than average. Anyway, so you know how I'm always telling you dad jokes, and I know you just love those, right? And and I'll also be telling you some math jokes and so on as well. But let me tell you something, just so you know, geometry, that's where I draw the line. Okay, let's start with a poll, and we had a lively discussion among the production team and a guest member, Bob Ward, and some folks were a little clueless on our own team about our logo. And I designed this logo. I'm pretty proud of it. And I was a little upset that some folks didn't quite understand it. I mean, especially this bit here, apparently was giving some folks some pause. And so I thought we might do a poll today, and our producer, Marisa, is going to help us do this poll thing. So, and if you can't figure out the poll, just put in the comments your sort of vote. So the thing that's circled, is that A, Buck's beard, B, Buck's head, or C, the shark mouth from the movie Jaws? I think what we'll do, let's give a moment or two for everybody to jump over to the poll and start answering that question. There's some pride writing on this particular poll, and there's some meat on the table as well. I've told Bob that if he loses his vote, that that he has to send me a tomahawk steak from. Remember when we went over to his ranch and we had that food and the steak was, that's the bet. I haven't decided what you send me when you lose, and we know which one is your vote. So, so choose wisely. Marisa, do we have thoughts here?
We do have the poll is posted.
Okay.
I can take a look and see.
Yeah, why don't you see what we got here? Because again, this is kind of an important thing. I know we're stealing some time here from our very important math discussion, but this is important, and this really is important. I spent a lot of time on this logo, and Marisa will attest that she spent far longer on it than she wanted to. What's the preliminary vote? Who's winning?
This is interesting. This is something we didn't consider. I'm not sure what the results of the poll are. I just know that it's open.
Okay.
So I could help out here.
Okay.
Awesome.
Marisa, our producer, is online. So Marisa, what do you know?
It's looking like 29% are voting for A, Buck's beard.
Okay.
43% for B, Buck's head, and 29% shark mouth from the movie Jaws.
Oh, that's awesome.
So
I love it.
Buck's head, B, is the winner right now.
Okay, so we will get a final tally maybe at the end. You've all disappointed me. You're all abject failures because Anna's winning right now. And that's just, now I have to send her like a Mickey Mouse shirt from Orlando, the proper Disney World. All right, well, I'll tell you what. Let's get started in the actual session here today. You know, we spend a lot of time, Anna, on predictions. But we really need to start with understanding the data first. Too much emphasis on predicting from the data set you have, like not understanding the data set, we can end up creating a bias. So if I do a poll of people who are watching the show on my logo, let's say, and only the people who like Anna are responding clearly, then obviously there's a bias there and they'll get the wrong answer. And so we actually need to test with more than what we have, don't you think?
Yeah, and maybe you could look at that data and at least confirm whether or not you're seeing any types of biases like that, which I might argue, you know, it's actually just a picture of your head and that's what it looks like.
Okay, well, we're going to do something a little more scientific than that. We're going to do something called exploratory data analysis, or EDA. Now I'm going to pop over to the most important source that you can have, which is going to be, let me see if I can find this. That's going to be Wikipedia, of course. So when you go to Wikipedia, which is, as we know, is completely reliable, actually, there's some really good stuff out there. It's a great place to start. It talks a lot about what exploratory data analysis is. So we want to definitely take a look at exploratory data analysis. And the reason why is doing an improper data examination of the sources and the treatments of the data can make you misinterpret and misapply the analysis, right? I mean, we need to look at this because, as you pointed out, Anna, they can get completely the wrong information with the logo and get the answer wrong, which is not what we want, sort of, at all. So there's some steps in exploratory data analysis, and that's really all this is. It's just running some steps around this stuff. And really, we're looking at two things. First, we start off with just verifying the source and the data, and that is very important to do. You have to verify where you got the data from and know more about that. And I'm going to give you a reference in just a few moments on how you can do that sort of thing. Now, all of our stuff, Anna, as you know, is in our GitHub site for this particular episode, and all the episodes are there. And we've got all the notebooks and all the links that we show are all there. So everybody's able to look at this. The first thing, you just look at the W's. And I taught my daughter this when she was younger. Whenever anyone tells you anything, who is telling me this? What are they telling me? And why are they telling me this? So we can just look at that data and how it was gathered. We'll know those things. Now, there's two kinds of things we get. Whenever you take and write down a bunch of data, like in a survey or a poll like this, that's called an observation. It's a group of measurements that we keep together. That's called an observation. And there's two types of data in an observation. The first is called qualitative or qualitative data, which is things like red, blue, green, the state of Florida, the country of Germany, and so on. And then there's also quantitative data, and quantitative data actually has numbers in it, and we can do math on that, on those numbers. And when we look at the data, we just kind of look at it. We're looking for things like missing values. Say we've collected a whole bunch of things, but maybe somebody's filled out some of the survey and not the rest. And we want to take a look at, did that get recorded sort of correctly? And we don't know. We could just say, well, then we're just going to ignore that whole observation. Well, that may be a bad idea. We may need that information. So the problem we have when we look at something like that is, should we put something in there? And the answer is, well, maybe we just put the average of all the other things. Maybe there's a lot of data and we just say, okay, we know they probably paid this much for this thing or whatever. We just stuff it in there. But then that makes the whole data set start looking more like the average, and maybe that's not what we want to do. Well, there's actually all kinds of math you can do to figure out what to do with missing values. We also want to want the minimum value, the lowest value, and the maximum value. That's called a range, so we can tell how wide the data is. And then we want to look at its shape, how many columns and so on. So we just want to do it. And Anna, I did all that for you. I put it in some my paper, but I didn't know how to get it on the computer. I was trying to hold it up to the screen, and it didn't do anything.
Oh, man.
So then I went on the internet, and my daughter helped me. I went on the internet, and I found this thing. It's this cool language. You should check it out. It's called R. It's the most amazing thing. I was able to connect to my SQL server. I'm using my big data cluster here, and I was able to load some data with a simple SQL query. So this R thing, look at this. I just typed in view right here, and look, here's all the data. Look at that. I can see all the data. Now, what is this? Well, this is from a company called AdventureWorks, and I basically went after their sales, and I'm really kind of interested in this tax amount based on like the subtotal or the total due. I wanted to do some work around that. So with this simple statement, I could do that. And then I found out in this R thing, you can run other things. Like for instance, I can get the range and I can quickly tell, I'm just going to paste that over there. I can get, and I see the range goes from 0.1 to 17,948. I can go get a summary of this data because now we're going to start getting into some of the things we can look at with our statistics. So I think what I want to do here, it's just so awesome to be able to do this. I'm going to pop over to our slides again, and we're going to start taking a look at everything we've got here. We're going to take a look at our clustering and our variability, and we're going to start using statistics. Our math for the day is going to be in the statistics world. Now, Anna,
before you get into that, you know, when you were showing R, like I usually use R Studio. What was that?
This is the R thing. It was on the computer.
Okay.
you can do, look at all the stuff you can do in the R. There's plotting. You can do all kinds of plotting with the R. Watch this. I'll just do a plot, and hold on a minute. I have to figure out how to move stuff around. There's a plot of the data. Look at that. Isn't that amazing? Look at the graphics on that. It's just
pretty cool.
Incredible. Yeah, it's very.
But it looks like you're using like 3 different IDEs. What's your IDE here?
My what? My idea?
Your IDE. So like your, what is it? Integrated developer. The tool you're using. What tool are you using?
This is the R. Yeah,
well,
R console. You got something better?
Okay, just the console.
You have something better?
Yeah. I mean, I think so. I mean, you know, every data scientist thinks their way is the only way and the best way, but
we'll get to your little voice later. All right. The point is, when we're looking at our data, it's way more important to stop thinking about looking at the data we have, the data we need, and the data we probably should have, right? And the first thing we need to do is just understand some of the proper data literacy techniques. So let me pop over to that next site I was telling you about. There's a full course here on data literacy, and I have this linked for everybody. It's a free course, and you can go through, and it takes you through all of those kinds of things, all of the data analysis. And this works everything from high school students all the way through CEOs. I've taught that particular course. So it's very useful to take a look at those things. Data literacy, super important. The first thing we need to know is there are statistics, Anna, then there's statistics, and then there's a statistic.
You couldn't have come up with different words, Buck?
I can't keep that many things in my head. So statistics are the numbers you saw, all the AdventureWorks stuff. That's the statistics of AdventureWorks. Then statistics is the branch of mathematical science that analyzes patterns of data and the ability to find those sorts of things. And then a statistic is a number about a thing. So that's how that works. And in some cases, remember we had those quantitative and qualitative statements. The quantitative is the number from quantity, and the qualitative is from quality. So it's a red ball. We can have one red ball, and we know that the 1 is the quantitative, and the red and the ball is the qualitative. But we can actually turn those into numbers as well. We can turn the qualitative into quantitative. And we did a little bit of that last time with the one hot encoding. Remember that? I told you about how I was often.
Yeah, please don't tell us again.
Okay, sorry. So the deal there is you do have these things that we need to take a look at all these things. There's two kinds of statistics, by the way. There's sort of descriptive and then inferential. And I'm doing a lot more of the descriptive right now, and later we'll get into the inferential parts. Descriptive means to describe, and the inferential means to infer. We look at one set of data and we move on to the next set of data. All right. So the first thing we do is the 3 M's, and we do the mean, which is the average. And there's several kinds of averages, by the way. And that's basically this formula here. You just take all the numbers, you add them up, and then you divide that by the number of numbers. That's it. I know it's a lot of stuff to write down just to say that. That's kind of how statistics works. There's a lot of Greek that they throw in there and Latin. So we look at that. That's called the mean. The other one is called the median. So if we order all the data, we can look at the middle one and we can say that's the middle. And you say, well, why do you need an average, a mean and a median? Why would you need both of those? Well, you may have an average of a certain number of coins in your pocket, but you may have more of one coin than the other. Out of the 10 coins, 8 of them may be dimes and one of them may be a quarter. So they'll average out to something, but the middle number will be a dime. You'll know that's the one that's in the middle. And in fact, there's another one called the mode, and the mode means the one that shows up the most often. And so we just need to know those numbers as we go through, because they're going to show us the clustering of our data. They're going to show us how things are sort of clustered. But that's not all that we need to think about. We need to also think about the deviation, or how things vary. And deviate means to turn away from. So basically, we have a formula we can use again that will show you how much the data in general wanders away from the average. And that's called a standard deviation. And that's basically a measure of the data on average from the average. In general, the lower the number of the standard deviation, the closer it is to average. And in a higher number of standard deviation, it means most of the data is not very average. So it's not as trustworthy to use the average for something. Now, we have something called a normal distribution. And I know that's probably one of the few times you'll hear me use the word normal. But a normal distribution looks like a curve, looks like a bell. I call it a bell-shaped curve. And a lot of things just happen to be that way. A lot of things are half to the left and half to the right. They make this nice curve. And so this particular thing will show you, the standard deviation will show you how fat that curve will be. Now, sometimes the curve sort of moves, right? And we've got a picture of a curve here. I'm going to move my mouse over and you should be able to see that. You can see that when we take these standard things, that about 34% of the data is one standard deviation away from the mean, and 34% is one standard deviation to the right of the mean, which of course basically means 68.2 ends up being within one standard deviation on either side. Less data, less data, less data. We'll be doing some formulas next week that try to see if something is in the range of what we should care about. Now, they're not always nice and pretty like this, right? Sometimes they're shifted, like there'll be more dimes like we talked about. And so that's called skew. Stick with me here, Anna, because this is a little confusing. Skew is how much the data moves from the normal distribution. If the values are farther to the right, we have more quarters than we do dimes, that's called negative skew or left. So farther to the right means left. It actually means left tail.
Right, because that's totally logical.
Right. And if it's the other way, then it's called a right skew because it moved to the left.
That just doesn't make sense.
Okay, that's just okay. You just have to. It has to do with the tail. It's a long story. I think the person was drinking a lot when they do that. Now we're going to measure that. There's a formula we're going to use called Pearson's moment coefficient of skewness. Isn't that just rolls off the tongue? We'll be learning more about that. There's also outliers. Now, sometimes the data doesn't cluster well together at all. We're looking at that sort of spread. So let me show you what an outlier might look like. I've got a picture of that here, I think. Here we go.
Is it a picture of you?
No, it's a picture of
sorry, I jumped the gun there.
Yeah, box plot. No, it's not my head, guys. It's something else. All right. So this is my favorite. Do you have a favorite visualization?
That's a hard one.
Yeah. Do you have one that like, oh, that shows me so much information at once? I don't know if our viewers do, but if you do, type that in the chat window.
Yeah, let us know your favorite visualization tool. I mean, I think the first one I look at is histograms. It's always the first one I use.
Histograms, yeah. Those are incredibly useful, showing the deal. I love a box plot. That's what this is called. This one's technically called a box and whiskers. This is the box and these are the whiskers. I can instantly see the range. This is the range right here, from here to here, where most of the data lives is between these things. I can see the quartiles when we take things and we chop them up into quarters. So we can see like the dimes and the quarters that we did. We can see how many of each is there. So that's this right here to here. That would be the quartile ranges that we can see. This is called the interquartile range. So if you divided your data up into 4, the first fourth is here, second fourth is here, third fourth is here, and fourth is there. And the red line is the average. So I just think this shows a ton of data. Not only that, it's got little pluses because in this huge data set that's being represented here, there were like a couple of things that were 90 and a couple of things that were below. So you wouldn't really care about them. Right? You wouldn't really care about them a great deal because they're what we call outliers. They're so infrequent. They're outliers. Now, sometimes we can't show things in that sort of very cool bell-shaped curve. We can't do that. And so for that, we use something called a scatter plot, which is just where you put the dots on the X and Y planes, and you can see how the data is. Even so, we'll be using this quite a bit in your machine learning sections, where we try to draw a line going through as much of this as we can. So that's kind of there. That's usually being called, there's no central tendency in the data. That's what that works with. But we'll cover that whole thing in another.
Hey, Buck, we got a lot of comments and questions, so I'm just going to share a few of them. A few people have asked about the link to our GitHub site, and that's been on the page for a while. It's just aka.ms/SOSN.
Here we go.
That stands for something old, something new, the name of the show, not a representation of us. And then the other questions that we've been getting, we've gotten some comments. Mala chimed in and said, box and whiskers for the win. So I guess she's a fan. And let's see. Someone else commented so many tools. And I think, there are a lot of tools, but I see it less as an overwhelming thing and more as, there's all these different tools and libraries and things people have already done for me to go kind of leverage. And we'll talk about that a little later. What do you think about the number of tools?
Yeah, it's always something that, and of course, working at Microsoft, right? We have 15 ways to do anything, and so a lot of times people just say, "Just give me one way to do something," but then that doesn't fit someone else, and so we add another one in. So this is a very old discipline. So we've gathered a lot of tools in our toolbox, but there's actually a link in that something old, something new for data analysis with Python. I think Python is some kind of language or something. Anyway, you can do with 2 lines of code everything that we're doing. So one tool, one library, and you're done. And it's really well done. And that's so as things are starting to mature, you're seeing those tools kind of be put into a single thing. So you will see this more often. But one of the things about working in this area is it's complicated. It's complicated because it's complicated. Speaking of complicated, Anna, let's jump from kindergarten to 4th year of college. Your data needs to go on a diet. This is the reduce, reuse, and recycle part. We need to, our EDA here, when we're doing our analysis and our exploratory data analysis and all that, it uses some really basic, easily understandable formulas. But for this next bit, we're going to have to level up on our math a little bit. Sorry about that. Specifically, the linear algebra. Remember, I talked about that in our last episode. You did do your homework out there from the GitHub site, right? You did do that, right? All right.
Yeah,
So,
I hope people did.
oh, I'm sure they did. I'm sure
they definitely did, right?
Yeah. Second they got done,
they listened to us.
They went out and did this. Okay. So Bruce Lee basically said one time, the best way to fight is not to fight. Isn't that awesome?
I don't understand. How can you fight without fighting?
So it was, you have to watch the movie Enter the Dragon, a stunningly amazing movie. And a guy wants to fight him and he doesn't want to fight. And so he tells the guy, okay, I'll fight you, but you get in a rowboat. We'll have to go out and fight off the ship. They were on a ship. The guy gets in the rowboat, he cuts the rope and the rowboat drifts away. And the guy looks at him and said, what'd you do? He said, the best way to fight is not to fight, right? And so what that means is with math, with what we're doing as well, the less of it you have to do, the faster it will be and the better it will outcome, right? So the less we have to deal with, the better. So we need to reduce the data, but we do need to keep the meaning at the same time. So we need to take a big spreadsheet and turn that into one cell. How could we do that, right? So let's assume I've got a spreadsheet with 1,000 numbers in it, but they're all 15. So I could take that entire spreadsheet that you would have to scroll through and I could put 2,000 times 15 in one cell. And I've lost neither the spread and I've not lost the frequencies, the number of times it happened, and I've not lost any meaning, but I've reduced the data I need to work with. Now there's a few ways that we have to do this inside our statistics. All right. There are three big sort of methods and there's things in them. So now we're gonna level up here and we need to move along to get you to your section. The first is the filter methods. And in a filter method, every feature, remember feature is just a number or an observation and features are just columns of data, is ranked based on some sort of metric. It's called a univariate or one metric that moves. And then it says the highest ranking feature is the one we'll keep, right? So you've got a bunch of things you need to bring with you on a trip and you're like, okay, I'm not going to need the parka because I'm going to Florida, so it's not going to be cold. So you don't bring that even though you need the parka someday, right? So we get rid of some of that data. Same kind of thing here. The way you do that is with various tools like variance is one tool, a thing called chi-square or chi-square. It's chi-square, but some people pronounce it chi-square. Correlation coefficients, information gain measurements, or mutual information. Mutual information is the one I just mentioned. So basically 15 times 1,000 or 1,000 times 15, if the numbers are all 15, then you don't need to repeat them. Just say there's 1,000 of those and so on. So those are called filter methods, and those are usually used first. They're just data we don't bring forward. The next one is called wrapper methods, and these select the numbers based on how well they help the algorithm we're trying to use, right? So there's two kind of approaches. One's called greedy, and it says I'm going to look at all of these and see how well they move the needle. And others are not called greedy, and basically they say, well, I'm going to pick some ones I think will work. And the ones you're thinking of, there's something called recursive feature elimination, sequential feature selection algorithms, and then even genetic algorithms. Genes tend to filter out things. They wrap around and say, I'm only going to select for the things that move the thing forward. And that's how our genes get propagated. And then finally, there's one called embedded methods. And these are interesting because when you're training your machine learning model, when you're actually in the training phase, it's grabbing data, chucking some out, and keeping some. That's why it's called embedded. And it can perform both the feature selection and the training phase in one step. And there's a few of these. There's three big ones. L1, it's called LASSO, L-A-S-S-O. That's an acronym, which is called a regularization method. Another regularization method is called L2 or ridge regularization. And then the one that's used a lot is decision trees. You know, who you're talking to and what you're going to say in your mind. You're doing this decision tree. Same kind of thing here. Now, within that, now we get into some math. So stay with me here, Anna. It's going to be okay.
You lost me at greedy. Now I was thinking about how greedy algorithms work and how they relate to me being greedy at one of those all-you-can-eat steak places. Like, I'm not going to go and eat everything and then say, oh, well, I really liked what I had before. I'm going to try to be greedy and pick the things I know that I like or that work for me. And I think that's kind of how greedy algorithms work too. So now I'm just a little hungry. So you kind of lost me, but
Yeah,
it's cool. We can keep going.
Yeah, you also do the filter method because we've been out to eat as a team before. And I noticed that you told me when we went to the Brazilian steakhouse, I went to the salad bar because it was amazing. And you're like, that's a rookie mistake. Don't fill up on salad. They're bringing steak. And so you did teach me there. That's a filter method. You said, I'm just filtering out. I know I don't want salad. There's no reason to go over there. But yes, you're correct. That's the way that works. All right. There's various tools we can use to do this. The wrappers, filters, and embedding. One of the main ones is called PCA, or Principal Component Analysis. So we have EDA, PCA, LDA, KDA, GDA, lots of A's that we're working with today. All right. Now, in our last episode, you showed people how to do a matrix math. And if you can get that covariance, things that move together at the same time out of a data set, you can make a covariance matrix. And then you compute the eigenvector of the matrix. Piece of cake.
Right. What's that?
Okay, let me show you what an eigenvector is. So an eigenvector is just from linear algebra, and it basically takes a line, it's called a linear transformation, and you change the data by a certain line. So let's take a look at the picture of Mona Lisa here. And when we see Mona Lisa, you can see there's a blue line and a red line, and we have shifted her back. We've let her lean back a little bit during the painting. And we did that by moving the red arrow, but not the blue one, because the blue doesn't change and we haven't lost the information in the picture. She's still there and working that way. That scalar factor is called an eigenvalue. And in this case, the line didn't move at all. So its eigenvalue is 1 and the eigenvector just moved it over a little bit. Now, here's what we can do with all those kinds of things. We can not only shift things left or right and so on, we can make them smaller. Because if I can make them grow bigger with these eigenvectors and eigenvalues, I can make them smaller too and allow my data to work that way. Not only that, I can reduce the dimensions of the data. So I can bring down the different things I need to look at. I can even use PCA to go from 3 dimensions to 2 dimensions and from 2 dimension to 1. Unbelievable. Now there's a whole world of this. And I've got all those inside the something old, something new place that we've got. And so that's basically what we've got there. Now, LDA is a little different. That's linear discriminant analysis. And that basically grabs the classes of data that are best related to the dependent variable. And it enters that into clusters. And you know my clustering mechanism. I've got one that we use when we're on trips. We've got things that are buckwoody and things that are not buckwoody. And that's the classes of things that I use. So it's heavily skewed, as we know. And so we've got that. And of course, you know, there's also, you know, there's others. There are all kind of math that you can do. What are you doing right now? Are you listening? What are you doing?
Oh, I'm just updating my playlist on Spotify.
While I'm talking.
Well, yeah, you got to keep the latest jams on your playlist.
You know, when I was younger, I used to have to dial the corded phone, call the radio station, get put on hold, talk to the disc jockey, and he would cue up a record for me. And I had to wind my alarm clock so I would know when that song was going to play so I could record it on my tape player.
I don't know what any of those words are, but anyways.
Well, I tell you
Let's take a look at some questions.
Well, let's put some questions, and then why don't you take over from here? So, I mean, if you're done with your playlist thing.
Yeah, playlist is updated. I can share the link with everyone later. But we got some questions. Neil Hambley, our dear friend, sent a message. I taught EDA using Jupyter notebooks, mainly with Python. What other tools do you recommend for students starting to perform EDA, and how much math knowledge is needed? Buck, I'll let you answer that one, and then I have some cool stuff to show them later.
Yeah, I mean, I'm the R guy here. I learned this R thing, which seems to be very cool. I think it just came out. It was only like 1969, 1970. So it was like last week. And so I'm ramping up on that. That is an amazing tool. So I use a lot of EDA methods and libraries inside of R, but I'm doing that just because I'm looking at the data statistically. And again, most of those, that 5num summary you saw me do and the summary function that you saw me do gets me to those things very quickly. And by the way, a lot of times it's hard to look at the numbers. You have to kind of look at, you remember the graphs and charts I was doing? I'm really proud of those graphs and charts I did, Anna. I don't know if you've got anything you can show that's to that quality or anything, but I'm pretty proud of those.
Yeah, I think you'll like some of the stuff that I have to show. But on our GitHub site, we also have a lot of resources. So if you want to learn some of our, best tips or go-tos for EDA, those will be there. We have a few comments from Steven Simon. One, he sent candlestick. I think maybe that means like it's lit.
I think a candlestick, there is a candlestick view of data.
Maybe that's what it was. He also mentioned while you were talking about PCA, are you talking about normalization?
So it can normalize the data. You can use PCA, which is a tool, to do all kinds of things. It's often used to do dimension reduction so that you just have to look at various things less. And again, when I say dimension now, most of you are familiar with business intelligence, and a dimension is the way you might look at data. So I can look at people in Montana who have green shoes. Those are different dimensions. I can look at green shoes, Montana, or the people who live there that have, and all those are dimensions. If the fact that they're wearing green shoes is not important, but the fact that they live in Montana is, then I don't need to look at that dimension, and PCA would help me drop that. But PCA is a technique you can use to do all kinds of things, including data regularization.
Awesome, thanks. And then a few other comments from Mala. She says, R is as amazing as Buck is. Wow.
Sure. A good reflection on R. I'm not sure.
Yeah, I'm not sure. But she also said, seriously, it's much easier to learn than Python, especially for a DBA.
I think personally, I think R is easier for a DBA, a database administrator, to learn. I think Python is easier for a developer to learn. That's been my experience. But either can use either.
I like both. I think there are certain things I like to do in R and certain things I like to do in Python, and kind of switch as you need them. There's some really great libraries in both.
Well, why don't you regale us with some of your amazing work that you've been done, and let's just see if you can. I just don't know if you can do the graphics as well as I did, but let's see what you've tried.
Yeah, definitely. I don't know if you saw the movie where they say anything you can do, I can do better. So we're going to try to do that today. Now, there are a bunch of tools that I use. I just wanted to show like some simple examples. I think, across what you're doing, you can use T-SQL, R, Python, and there are other languages too. Someone mentioned in the chat that they use .NET for this sort of thing. Lots of languages are coming up with various libraries and packages. I just find myself that, especially if you're a data professional, sometimes analyzing data with T-SQL is the easiest thing for you to do. And because of all the packages and the hype around R and Python, it can be very easy to find whatever it is you're trying to do on the internet and just kind of use it. And you'll see that I tend to do that a lot. I don't know if it's a millennial thing or like a normal thing, but like I don't do anything without the help of my favorite search engine.
I'm with that.
But I think when you're looking at the data and you're using T-SQL and R and Python, it's great to run all these different statistical analyses, but a really important piece of that is also looking at the data. So actually taking a look at the data. No, I don't mean like staring at the numbers, like visualizing the data. So, let's take a look at a very classic example that just kind of illustrates this point. And again, this is all part of our GitHub page. But we're going to go through an example called Anscombe's Quartet. And this is a very popular example. And it's basically 4 data sets with the same mean, standard deviation, and regression line. So let's take a look at this. So what you can see, I'm just using some of my favorite packages for plotting, matplotlib.pyplot, and also NumPy. These are 2 great packages that most Python users use pretty extensively. I just put in some data sets. And you can see I just have 4 of those different data sets.
Okay, gotcha.
Now, what I did is I took the mean, the standard deviation, and the correlation coefficient. So correlation coefficient, you talked about this as well, Buck, but like if you think about linear regression, or if you take it back even one step further to y equals mx plus b, the correlation coefficient is going to be the m, or the slope in this case. So what I did is I took these numbers, and you can see each set of numbers is pretty different.
Okay.
But you might see something interesting in the mean, standard deviation, and correlation coefficients.
Yeah, okay. So I would say, because I'm a numbers guy, I like to just read text. I think these data sets are roughly the same. I would say they look the same.
Yeah, and you would be right in saying that based on this analysis, because all of these numbers, the values for the mean, standard deviation, and correlation coefficient are different.
They all look the same. All have the same standard deviation, roughly, same mean, median, mode, all those. Yeah, I like it.
Must be the same. What happens though is you can actually plot these values.
Okay.
And what you'll see is data set 1, 2, 3, 4. Now tell me, do these look the same?
Oh, wow. No, they're dramatically different, aren't they? Wow. I mean, 1 and 4, if you were to look at the graph, you would say they have nothing in common.
Right.
Wow. That's impressive. So this kind of proves that you need to not only look at the numbers, the text, and my handy paperwork, but you also need to plot it out and see it in graphics, don't you?
Yeah, exactly. So this exploratory data analysis really involves a lot of different things. We did get a question from Mike B, and I'm not sure exactly what he was referring to, but he says a Python EDA command was mentioned. Can you provide the name of that command? Did you name one?
I didn't name a specific. I mentioned that there's this library you can get that in 2 lines of code, you get everything you need for EDA. That is in the something old, something new repository, aka.ms/SOSN, that one right there. And take a look at that, and you'll see a link down in there under the EDA section for this episode that shows that. And it's got a live example. I'm so impressed with this thing.
Yeah, we took a look at that earlier this week. It was actually really cool.
Yeah, it's really nicely done.
So check that out. Okay, cool. So that's Anscombe's quartet. And again, just kind of proves that, you should be looking at the data in like visualizing the data in addition to analyzing the data, just with math. Okay, so let's move on and let's talk about some different tools as it relates to Azure and SQL Server and Azure SQL and that sort of thing. So the first tool I wanted to mention is Azure Cognitive Services. Now, I worked a lot with cognitive services in the past few years, and one of the great things about Azure Cognitive Services is that it takes years and years of Microsoft research, and they put them into these really easy to use APIs. So as a developer, instead of having to build and train these models, you can basically use them. There are models around image recognition and classification. There are models around language detection, translation, searching. There's all sorts of different cognitive services available. They're really easy to use, and you don't have to be a data scientist at all. We also have Azure Synapse, and we like to call this AI at scale. So if you're doing really, really large scale analytics, then Azure Synapse and all the tools and packages and interfaces that go along with that are really going to help you. And then we have Azure Machine Learning, and this is if you want to do web-based AI. And so this could mean your data is coming from somewhere else. Maybe your data is in Synapse. Maybe your data is in Azure SQL. You're going to kind of import that data for the analysis you're going to be using, and then do machine learning on that. However, there is something that I think is slightly better than this in some cases where it applies, and that is this ability of built-in machine learning, which is in SQL Server, as well as in Azure SQL Managed Instance. So let's talk about that just a little bit. So setting this up is really easy on SQL Server. You basically go into the SQL Server setup, and you're just going to check the boxes for R and Python. We're going to enable those capabilities for you, and you can start doing that analysis in T-SQL or in Python or R, and I have a cool example for that. Now, if we take a step back and say, well, what is actually happening when we do this, and why do you say that it's better? Now, remember a previous scenario where what you're having to do is you're going to have to move all your data from wherever it is, then do machine learning, and then bring the model back or whatever else you want back, and you have to keep moving that data every time you want to retrain the model. that can be very workload intensive, as well as, every time you move data around, you have the opportunity to kind of change the data, mess up the data, lose the fidelity of the data. Lots of things can go wrong in moving data. So one of the great things about machine learning services in SQL Server and Azure SQL Managed Instance is that we actually do in-database machine learning. So what this means is you don't actually have to move the data. What we're able to do is we've separated out these services for you, and here you can just see the architectures for Windows and Linux. But basically, it has its own processes, the R Python workloads, and they're able to do machine learning on the data in the database without you having to move it out. So this can be really useful. We had some security things that made this architecture very important.
Awesome. And I see it's different slightly for Windows and Linux, and that makes sense. So like I did with the R, you don't have to query the data and bring it all the way across the network, work with it on your local coal-powered, steam-powered machine, and then try to limp it through. You can actually write the code in R or Python, and SQL will do that on the server for me.
Yeah, exactly. Okay. And it gets better than that because we're always working towards making this a little bit easier. So okay. I'm going to hop back to Azure Data Studio. I wanted to show you something that was recently released. It's called the Machine Learning Extension. Now, what this is it's an extension specifically for Azure SQL Managed Instance or SQL Server, wherever it's hosted, whether it's on-prem or on Azure. And what it's going to do is basically help you do various things. So what I wanted to do is I have this managed instance running here. I can just select manage, and it's going to bring up kind of my overview pane for that. And what I see on the left is I now have this machine learning tab. Now, this is going to allow me to do many things like manage the packages in the database. So no longer dealing with the hassle of trying to figure out where those packages are located on the SQL Server or managed instance system and adding them there and making sure they're the right version and all that stuff. You can manage it all with this little tool. And then the other thing it does, let's see, so it's coming up. The other thing, I'm just going to close out of this, but the other thing it allows you to do is make predictions right from here. You can see your existing models, so it's going to be able to find your table where you have models stored, or you can navigate to it. You can also import models from other places. So we talked about this last time, how you can kind of train in one place and deploy to another place. So if you train this model in Azure Machine Learning, you can still import it here on your Azure SQL Managed Instance.
Well, this is very cool. I might have to start using this instead of the blue thing I've got.
Yeah, it's pretty cool. And I think, excuse me, a little bit easier to use than the blue thing that you got. Another thing you can see here, there's some examples. If you want to hear me talk more, there's a video here. But okay, let's talk about how that looks. So once you've enabled this, so I have this enabled on my managed instance, and I have a much longer example, but I just wanted to show you that once it's here, you can start to do some analysis, and you can even start to train your models in the database. And you can even deploy those models using T-SQL. So here you can see I'm creating an external script that's leveraging the Python language, and it's basically going to create the model in the database, and I can then deploy it and make predictions. There's a lot in here that I'm not going to go through today, but it's pretty cool, very useful, I think, for doing machine learning.
Cool. I love it. I love it. I like that it's more secure and it's going to perform better because the data doesn't have to go across the network. And the other thing is I can like create all this on my local laptop, get all my R or Python the way I want it. I can hand it to the DBA. They can then run it. They don't have to know R or Python if they don't want to. And then they can put that in a stored procedure. And so their users now can make predictions from the data that's on the database that I didn't, as the data scientist, I didn't see it.
Yeah, exactly. I think security is like a really key highlight of these capabilities.
Very impressive.
Now, one question we got from Geek SQL is this only in managed instance? So I wanted to clarify this specific capability that I'm talking about is available in SQL Server, wherever SQL Server is running, as well as in Azure SQL Managed Instance for R and Python.
Right. So on-prem, as a VM, all that kind of stuff. If you've got SQL Server running, these features are capable of doing it.
Definitely.
Yep.
Now, as we kind of move forward, I did want to talk about this reduce, reuse, recycle thing you talked about, as well as eigenvalues and eigenvectors. And I think the biggest reason you would go towards these is for dimension reductionality or dimensionality reduction. Where you put the ality is kind of up to you. They're made up words. They're not real words. But this is really important because we've seen, Buck was talking about some examples where you have a bunch of the same number, but it's possible that you have a data set that has, 15,000 features to select from. So even before you go and run, any sort of actual machine learning or actually trying to find linear regression or those sorts of things, like you're going to want to reduce some of the dimensions that you have. So this is a really important practice, really important for making your data more manageable, but still equally useful. So this is really important. Whoops, that's not where I wanted to go. This is really important, and I wanted to show you just the simplest example because I don't think walking through an example where we have 15,000 features is necessary, but maybe when we have more than we want. So going to bring up this example. Now, this is kind of a classic data set. Now, everyone's familiar with the IRIS data set. When you start to use machine learning and even getting into deep learning, because oftentimes that's what this leads to, because you just have so much data that you need more compute power and you need more analyses. But this IRIS data set is very popular. It basically takes in 4 measurements. So it has 4 features related to, the sepal length, the sepal width, the petal length, and the petal width, and it's trying to basically classify flowers. So you're seeing these.
This is Python, and that data set's built right in. Are you saying this notebook is out on our GitHub? Would I be able to run this myself?
Yeah, so this is something you could run yourself. This is all out on our GitHub, so you can try it yourself and play with this and even do some more with it. Because really what I'm doing here is I'm just getting started. So this example is using PCA, so principal component analysis. So like Buck, you were mentioning earlier, where we're basically trying to reduce the number of dimensions. So here we have 4 dimensions. Again, this is a very simple example. You could have thousands here. And what we want to do is we want to turn this into just 2 features. So what we're going to do is we're going to bring in your favorite packages. So scikit-learn is one of my favorite packages in Python. It's just so easy to use, and they have a lot of stuff in it, especially when you're getting started. So what I'm doing here is I'm just identifying the features. So I mentioned we had 4 features. And then, of course, the label is going to be what they're calling here is the target, but the label is basically going to be what we're trying to predict. Okay. And then what I'm going to do is I'm going to scale the data. So this is pretty important. So what you can see here is each data set, each feature has, fairly different values. Like this is, almost an order of magnitude bigger than the width value. So what we want to do is so that all features kind of remain equal, we want to first scale the data. So you can do this or standardize the data, which we can do with standard scaler.
Okay.
And now you can see they're all kind of more in the same range of values.
Okay, that makes sense.
Now, again, using sklearn, I'm just using the simplest way to do PCA, which is just using the package PCA. And what I'm going to do is I'm going to go ahead and find the principal components by using pca.fit transform. Again, it's very straightforward to use these packages. And then I'm going to grab the results from that, and I'm just going to grab the first 2 principal components. So the first principal component is going to contain the most amount of information. So basically, it's going to be the most useful component, and then the second one is the second most useful. And depending on how many principal components you want to use, you can kind of cover more variants like you were talking about before. And it just kind of depends on what you're going for. But for this one, we're just going to look at the first 2. And again, this is all part of the, more of the data engineering, data prep. We're not really doing any machine learning yet.
Sure.
Now, when I plot this, I'm going to go one smaller. When I plot this, what you're going to see is I have principal component 1 on the x-axis and principal component 2 on the y-axis. So we're no longer tracking sepal length, sepal width, petal length, petal width. We're just looking at principal component 1 and principal component 2. And what's really interesting about this is it does a really good job of separating out, I mean, this is a little marginal, but a pretty good job of separating out the different types of flowers just based on those principal components.
Very cool. Now go back up to the very top of this, if you will. And I noticed the logo is completely different. Apparently, you know, this is the one that I think people would understand better and would not get wrong, like when they picked yours, which was wrong. And I predicted that they would, I used some PCA and some LDA, and I did a prediction that the audience would get confused. And I redid our logo. So you'll see that new logo start showing up to where it doesn't look like my head. My head, really, people, my head. So anyway, I did a prediction. So that's where that came from. And also, and the primary component I knew is they like you better. And so they didn't think it looked like my head. They just know that that's what you would have picked, and they like you.
Yeah. Well, what can I say?
I know. Yeah, that was the PCA. Yeah.
The only final thing I wanted to call out about PCA is like, now that we've taken this into 2 components, it's going to be super easy for us to use machine learning to create a model that's going to separate these. So that's going to be really helpful in reducing the dimensions and improving both the accuracy and performance of your machine learning models.
Excellent. And so again, the whole point of this is to figure out what kind of flower am I looking at. So you took a 4D and you turned it into 2D. That's amazing. Our brain does that with pictures. We look at a picture, which is one-dimensional. It's just a picture. It's flat. And we turn it into 3 dimensions in our head. We see perspective and so on. This is the opposite of that. You just took something and flattened it up for us. And the possibilities are just absolutely endless with what we could do. And you could have even gotten it down to 1 dimension, really, if you wanted to. Might not be, but we call that, it might not perform as well. When we use the word perform in data science or specifically in machine learning, we don't mean how fast, we mean how well. So when we say that has a good performance, we don't mean that it runs quickly. In fact, it may run much longer. We just mean it works better because it predicts with more accuracy and recall that we want.
Definitely. Yeah. And I definitely agree. There's lots that we could do here. I just wanted to call out one word of caution. When we talk about principal components, or you see us use PC1, PC2 often, that is different from p-value. Is that correct, Beck?
That's different. Yeah, that's different. So we will talk about p-value. A p-value is a statistical concept, and it's often misused. It's a very valuable concept. It has to do with that standard deviation and normal distribution that we saw. We can do a p-value to see if we're going to accept a hypothesis or not. While it may be used within this, the PCA is separated and different. PCA is a technique, and it's a particular algorithm or set of algorithms that uses those eigenvalues and eigenvectors. And there's some really good things out there. Eigenvalues and eigenvectors are actually not hard to understand, but there's 4 kinds of math that go into them, matrix multiplication and other things that can be hard to understand. So most people are fine with eigenvalues and eigenvectors once they understand the 4 things that makes them up. And we've got lots of links and things out there for you on aka.ms/SOSN. We try to make sure every time we put something up like Anna's got, we put that inside the GitHub for you there, so you'll have a place to go back to and try those.
Yeah, definitely. And, you know, we're kind of wrapping up the show here. We're really excited for next episode. Buck's going to work on his green screen because I think maybe he's getting that's not how green screens are supposed to look on camera. But
it said green screen, so I put up a green screen. I don't know. It's very confusing. It seems like they should just say what they mean, like left skew and right skew. Just
right, exactly. Yeah, very logical. You know, it makes sense, you know, that you are an outlier in this space.
It does. You know, Anna, it's been fun as usual. I love these. They're tons of fun. Hopefully everybody else is enjoying them. We are recording them. And if you go to SOSN, the link there, you'll actually find a list of all the video episodes and so on. And after this one processes, we'll have that recorded up as well. And if you don't have any other questions for us right now, I think, Anna, we should probably turn it over to our producer, our Steven Spielberg level producer, Marisa Priscilla.
Yeah, definitely. We'll pass to Marisa. You know, if you like this video, please subscribe to our channel on YouTube. It's just Azure SQL YouTube. And we hope to see you next week on Data Exposed.
Thanks everyone for joining in this week's episode of Something Old, Something New with Anna Hoffman and Buck Woody. I want to give a special thanks to Wolfgang Pauli, Jeremy Reynolds, Tampa Bay, Learn TV, Channel 9, and as always, Anna Hoffman, who's the host of this show, and myself, Marisa Brazili. Find a complete list of episodes at ak.ms/somethingold-something-new -videos, and then you can find the GitHub at ak.ms/SOSN. Thank you all.